So banker's algorithm is used as a deadlock avoidance algorithm. Okay. Now, what is deadlock? Deadlock is what? A set of block processes, each holding a resource and waiting to acquire a resource held by another process in the set. Right. So, deadlock is what? A set of block processes, each holding a resource and waiting to acquire resource which are held by another process in a set, right? So to avoid this deadlock, algorithm used is banker's algorithm. Okay. Now, this banker's algorithm can be used when resource has multiple instances. Okay. Say printer is a resource, right? So if more than one printer is attached to a system, then you can say the system has multiple instances of printer, right? So in that case, you can use this banker's algorithm. Second rule is that each process must prior claim maximum use of the resources. So if a process has to complete the execution, or when it's going to start the execution, before it starts its execution, it has to uh, claim that how many resources are required, maximum number of resources are required to complete the process execution. That must be declared prior itself. Okay. And the next point is, when a process requests a resource, it may have to wait, because the particular resource may be used by any other process in the set. Okay. And the last thing is, when a process gets all its resources, all the required resources, then it must return all of them in a finite amount of time. So if any process need four resources to complete the execution, then once it acquires all the resources, it has to be written back to the operating system, or it has to release those resources within finite amount of time. So this is the introduction about the banker's algorithm. To implement this banker's algorithm, you need certain data structure. Okay, that is, the first one is available. Okay, that means how many instances of resources of a particular type will be available. So at a given point of time, how many instances of a particular resource are available? That is, to represent that, one data structure is used. And then is the maximum, that is max. It says that what is the maximum number of resources required for the process. That is one more. And then allocation. Allocation data structure says at a given point of time, at a current time, how many instances of a particular resource has been allocated. That is third one. And the last one is need matrix, you can say. That is, how many more instances of a particular resource type are required to complete the task or to complete the process execution. That is called as need. Okay. And the formula you have to remember to find need matrix is that maximum minus allocation. That is, maximum requirement of the resource instances minus currently allocated instances of the resources. If you subtract these two, you will get need matrix for the set of processes. Okay, these are the data structure used to implement banker's algorithm. Fine. Now we'll see the algorithm used in banker's algorithm. That means the first one is safety algorithm, which we are going to implement using Java code. Okay. The first step is, first we will use work and finish. Okay. As two vectors of length m and n respectively. Initialize work is equal to available. So I'm considering a vector called work, and I'm assigning this work with available. Available is what? At a given point of time, how many resource instances are available. That is okay. And finish of I, that means initially I will assign all the processes as false only. If there are 10 processes in a set, I'll assign all the processes finish state as false itself. That means none of the processes have completed its execution. Okay, next. Second step is that you have to find I such that finish of I is equal to false. You have to choose the process where the finish of I value is false and need. Need is what? How many more instances of resource type is required to complete the execution of a process. That one. Okay. Need is lesser than or equal to work. What is work? That is available here. Okay. You have to choose the process where finish of I is equal to false, need of I is lesser than or equal to work. Okay. Then if this such I exists, okay, then you have to update work value, that is work plus allocation. Work is the one which is available here. Allocation is what? Allocation of the particular process which you chosen here. Okay. That means at a given point of time, how many instances of a resource type are allocated, that you have to add it up. If no such I exists, if no such process exists, then you have to go to step 4. That is finish of I is equal to true. That means all finished state of all the process is true, then the system is in a safe state. Here, that is at step 3, after adding finish of I, you can assign it to true and again go to step 2 to find the next process so that you can complete the execution of rest all processes. Okay, this is the algorithm need to be followed to implement Banker's algorithm. Okay, so now let's solve the problem. So consider this is the given snapshot of the process state. Okay, so at a given point of time, number of processes given 5, that is P0 to P4. At this at a given point of time, allocation is what? At this particular point of time, how many resources are assigned? Okay, that is what. Here, 3 types of resources are used. A, type B, type C. And each type have different instances. You have to remember. A may have more than one instance, B may have more than one instance, C can have more than one instance. Okay. Then next column is maximum. Maximum says how many instances of a particular resource is required to complete the execution of P0. See here, at a given point of time, allocation of A resource type is 0. B, one instance has been allocated. With respect to C, 0. But maximum requirement for completion of P0 is what? 7 instances of type A resource is required. 5 instances of resource type B is required. 3 instances of resource type C is required. Okay, this is the maximum requirement, out of which this much has already assigned. Now you have to find out need. How many more instances of each resource type is required? Then you minus this and this. 7 minus 0, 7. 5 minus 1, 4. 3 minus 0 is 0. Okay, this is the need matrix of this process. Okay, at the given point of time, the available resources are 3 instances of resource type A, 3 instances of resource type B, 2 instances of resource type C. Okay, in the same way, for all the processes, what is its allocation, what is its maximum, and what is its need is given. See, only allocation and maximum value will be given. You have to find out need. That is subtract max minus allocation. Okay. So that is how you have to consider. So with this information, we'll solve the problem. So this problem is solved according to the algorithm which I explained in the previous slide. Okay, first you have to consider how many processes are there and how many resources are there. Okay, initially step one, what it says, work will be assigned to available, right? So available is what? With respect to this 332. So that is 332, and I'm initializing all the processes as false. Okay, next I is equal to 0. That is first process. Consider this first process. Allocation is what? 0, 1, 0, right? And need is what? 7, 4, 3, right? So that is what considered here. Check whether the need is, you have to remember this algorithm. All the processes are initialized to false. That is right? You have to check for the particular process, the need is lesser than or equal to work. Need is lesser than, here, see here, need is 743. Is it lesser than or equal to work? Work is what? 332. It is not lesser, right? 7 instances of resource type A is required, but available is 3. Here 4 is required, available is 3. Here 3 is required, available is only 2. So at this instant, this first process cannot be executed. Okay. Next, increment I value. Consider the next process. What is its requirement? Need 1, 2, 2. Right. So now 1, 2, 2. Check with work. Is it lesser? Yes, it is. So you can assign what the required instances of resource type for this process and complete the execution. That's why the tick mark is given here. Okay, so this process completes its execution. That is process 1 here, this one. Okay, once this process completes its execution by acquiring all the required resources, then it has to release all its resources. Okay, once the process completes its execution, it has to release all its resources. Okay, that is uh, uh, how can you do it? Work plus allocation. That is this third step, work plus allocation. That is written here. Work plus allocation. Work is 332. 332, for which you have to add allocation. Allocation is how much? 200. That is 200. You add 3 plus 2 is 5. 3 plus 0 is 3. 2 plus 0 is 2. Okay. And then assign finish is equal to true. Okay. In this way, you have to find out whether the particular process can be assigned with the required resource type or not. If it is possible, then uh, uh, give all the available resources to the process. Let process completes its execution. Once the process completes its execution, it has to release all the acquired resources. Okay. And then you have to find out the safe sequence. I mean, the order in which processes are assigned with the resources and completes the execution. And with respect to this problem, P1, P3, P4, P0, P2 is the order in which the processes completes its execution, and it will be in safe state. That means there is no deadlock. You can avoid deadlock by following Banker's algorithm. Okay, I hope you all follow this. Now we'll see uh, the explanation by considering the example, the same example. Now, just I'm using this. P0 will be watermarked as 0, P1 watermarked as 1, P2 as 2, P3 as 3, P4 as 4. Okay, and I'll be using resource type with the filled red circle, B with filled green circle, and C with the filled purple. Okay, or gray, whatever. Okay, and the available will be represented in this box. Okay, and this hollow box, the respective colors only used. Okay, hollow circles will represent the need of particular resource. Okay, the filled one is already assigned resources. Hollow circles are those are required for the process. Okay, let's see the first simulation. See here, available is 3. Resource A, 3 instances are available. B, 3 instances are available. C, 2 instances are available. Okay, and this is the given problem where need matrix is updated. Now, let's consider the first process, that is P0. For P0, how many resources are required? 7 with respect to A, that is red hollow circles here. 5 green, and this purple or any color, I don't know, this color 3. Okay, and here this represent the required one and this represents already assigned one. Now you just see this is required, right? You have to check available, is it greater than need? Okay, so you have to check this condition, or need is lesser than or equal to available. Okay, that condition you have to check. Now you just see allocation is what? One is a resource type B is assigned with 1, right? So out of 5, 1 is assigned at a given point of time. Okay, next. When you compare this, when need compare with what? Yeah, you have to check here how many instances of resource type A is required. 7. That is not available here. Check 4. It requires, right? Only 3 is available. 3 is required. Only 2 is available. So it can't be executed. The process. Okay. Next, come to next process. The requirement is 3. With respect to B, 2. With respect to C, 2. Can it be satisfied with the available one? Yes, you can satisfy, right? So that's why these are assigned. This first thing is allocation. 2 is already assigned out of 3. So only one it is required. It compares, yes, and it can be assigned. That is, 1 is as allocated, 2 is given, and then for C is also given. Okay, so now it is assigned and it completes its execution. After it completes its execution, it has to release all the resources to available here. See, this completes execution and it releases all the resources to available. Okay, now this is the new set of available. Okay, you can see here it is updated. Now next comes P2. Okay, it requires how many? 9 resource type A, and this is 0. Sorry, this is 0 and C as 2. Okay, out of which 3 is already assigned. 3 is already assigned. 2 with respect to C is already assigned. Can it be solved with the available resources? This requires 6, right? So that can't be satisfied. So this can't be executed. Now comes 3. Maximum is 2. This is 2. This is 2, right? Out of which 2 is already assigned, 1 is already assigned, and 1 is already assigned. With the available resource, you can serve this request, right? So it is possible you're going to use those resource. It completes its execution by having all the resources. After execution, it will release all the acquired resources to the available. Okay, and then you can see available is updated, and P4 where the required is 433 out of which only C is assigned, right? See, C is assigned. Yes, when you compare with available, the request can be satisfied. and it will give 4 instances of resource type A, 3 instances of resource type B, and 1 instances of resource type C. And then it completes its execution, and then it will release all the acquired resources. Right? Now you can see available is updated. Now still we have not completed P0, right? Because resources were not available, right? Now again consider that process. The request is 753, out of which only B is assigned 1. Okay, now you can serve the request with the available resources. Compare it. Yes, it is possible. Assign all the required resources, and then it completes its execution. After completing, it will release all its claimed resources, and then available is updated. Okay, and then P2 was not executed, right? The requirement is 902, out of which 3 and 2 were assigned. 3 and 2. Now you can serve the request with available resources. Yes, and then it can acquire the required resources and then complete its execution, right? And after completing, it will releases all its resources. Okay, then you can see all the process completes its execution. Right, now this is the initial given snapshot, and this is the final uh, snapshot once the process completes its execution. Okay, now calculate, I mean, how to verify whether have you assigned proper resources so that process could complete the execution, right? So how to first calculate total initial allocation, that is initial allocation. You calculate this, that comes to 725. Okay, and then add initial available is this one. So this plus this should give you this value. Okay, so that comes to 1057. So it is proper. Okay, that's all about the example explanation under Banker's algorithm. Now we'll see the coding part. Yeah. Okay. So in the main function, I'm just calling Banker's function. Okay. So I'll directly go to the Banker's class. Okay, I'm using all the required arrays. Need matrix I need, allocation I need, maximum matrix I need, and available, and number of process and number of resources. So these variables I have declared. Now we are in the input function. I'm entering the number of processes and the resources, that is NP and NR. Next, initialize the array. Need matrix, maximum matrix, allocation matrix, and available. Okay, so now you have to read once you read the number of processes and the resources, you have to read values for the allocation matrix. That is, here you can see this first. Where is the problem? Here, this one, allocation. I hope this one, allocation. Okay, this you have to read it from the keyboard, and this one also from the keyboard, I mean from the user. Okay, so that is what I'm doing here. I'm reading allocation for each process and how many instances for each resource type. Okay, and then enter maximum matrix, the same, how many process for each process you have to read how many instances of each resources required. Okay, after that you have to enter available matrix. Available matrix is what? This one. At a given point of time, what is the available matrix? That is also you have to read it from the input device or from the user. Okay, that is what available matrix. Then once you have the allocation and the maximum matrix, you have to find out the need matrix. How do you calculate need matrix? Maximum minus allocation. So that will give you need matrix. So this is already explained in the slide, right? So this one, need is equal to maximum minus allocation. So and then we will check like if all resources required for the process can be allocated. So whatever we checked here, we are going to check where here we are going to check the available can satisfy the requirement, right? This we are doing at this function. Check, is this available lesser than need? Okay, so that you are going to check it out here. Okay, and then we will first will call the input. You will take the readings from the input, then you will calculate need matrix. Okay, and then you will check what whether resource can be allocated for the processes. Okay, initially, so for this I'm considering the while loop, and I'm checking for each process till all the process completes its allocation. Initially the allocated will be assigned to false, and then I'm just checking. If it is not done, then check of I. Check of I is what? This one, whether available is lesser than need. Okay, so that is you're going to check, and then if it is true, then you will try to allocate the resources for the each process. Okay, then once you allocate it, you are going to calculate the available as available minus need plus maximum allocation. Okay, this will give you the available. Fine. So and then you are going to print out the allocated, which process is allocated with the resources. Okay, and then once you allocate all the required resources to the process, then you are going to change the allocated to true. Okay, and then increment j to consider the next process. Okay, if it is not allocated, then break. Okay, then if j is equal to np for all the processes assigned with the required resources, then you will say all the processes are assigned with the required resources and it is safely allocated. If not, all the processes cannot be allocated safely. Okay, that's all about the explanation of code. If you understand the explanation theory part well, then it is easier for you to understand the coding part.